Good day again, class. And the topic that I will discuss to you today is on statistical analysis. And these are my learning objectives. The learning objectives for today's session, that at the end you should be able to discuss the principles behind statistical tests and then identify the statistical tests that you need to use given a particular specific objective. And this will be the outline for my presentation. So we'll be talking of the principles behind statistical tests and then identifying what statistical tests to use. Okay. The statistical tests that we need to use or that we have to use in our study depends largely on the objectives of the study. And the statistical test is done to really answer the objectives of the study. And when we talk of statistical tests, we have descriptive statistics if our objectives are descriptive objectives. Then we use the test of hypothesis if our objectives are analytic objectives. Now, for descriptive statistics, when data are qualitative data, and I would like to believe that you already know the meaning of qualitative data, the statistical test to use will be frequency and percentage. And the 95% confidence interval of the frequency will also be calculated. Now, so let's give an example. If this is the objective of the study to determine the prevalence of zinc deficiency among patients with diabetes mellitus, we use, this is a descriptive statistics, we use frequency and percentage of people who have, or the prevalence or percentage of people who have zinc deficiency, and that is the prevalence, and then the 95% confidence interval of the percentage or of the prevalence. Now, for quantitative data, so we talk of the mean and the standard deviation. And we can also calculate the 95% confidence interval of the mean. So, for example, if this is our objective to determine the baseline central retinal thickness among patients given Avastin, so central retinal thickness is a quantitative variable, and so we use the mean and the standard deviation, and we can also calculate the 95% confidence interval of the mean. Now, when we only describe data in a population without adjusting for some factors, you are normally making a descriptive statistics. And if you are making a comparison of the outcome in groups, we cannot make a valid conclusion with regard to the comparison in a descriptive statistics, because as we said, descriptive statistics does not intend to make a comparison. Let's give an example. So the crude death rate of a country by country in 2019 in the Philippines is 6 per 1,000 population, meaning there are 6 people who died in 2019 per 1,000 population, per 1,000 population. So in Japan, 11 per 1,000 population. In Germany, 11 people died in 2019 per 1,000 population. In UK, 9, USA, 9. These are just descriptive statistics. We cannot make a comparison as regards to the crude death rate of these different countries. You will note, for example, that the Philippines has the lowest crude death rate in all of these 5 countries that I have presented here. But that does not mean that we have better health quality, better health service in the Philippines. And the reason for this is that this crude death rate did not look into the factor that can affect. We did not adjust the age, I should say. We did not adjust the age here. You will note that in the Philippines, we have the population is young. In Japan, in Germany, in UK, in USA, the population is old. And that's the reason why there are many or the higher crude death rate in Japan or in Germany or in UK and USA compared to the Philippines, precisely because their population is old. And of course, if the population is old, there will be many people who will die. So when we talk of crude death rate, not adjusting for the age, then you won't be able to make a comparison. Okay, let's move on to analytic statistics for analytic objectives. So we use the test of hypothesis. And when we talk of test of hypothesis, we have the independent and the dependent variables. And we can also talk of confounders. And when we talk of independent and dependent variables, we are talking of an analytic objective. We can only talk of dependent and independent variable in analytic objectives. So, and in the test of hypothesis, we have the univariate and we have the multivariate statistics. Okay, what does univariate statistics mean? When we say univariate statistics, we only have one independent and one dependent variable. So, with multivariate statistics, we have many independent variables, including the confounders, and one dependent variable. Okay, let's give an example of an analytic objective. This is the objective of the study to determine the relationship between height and cardiovascular disease. Now, to answer this objective, a univariate analysis will need to be made initially. Univariate analysis, uni means one, is looking at one independent variable, and in this particular objective, the independent variable is height, and one dependent variable, the cardiovascular disease, without considering other variables that can affect the relationship. Just look at height. People, we might want to categorize people as to whether they are tall or short. So we just look into that variable. We just group people into whether they are tall or small, and then we look into whether they have cardiovascular disease. Among the tall, how many of them have cardiovascular disease? Among the short, how many of them have cardiovascular disease? We just look into height without considering other variables that can affect cardiovascular disease. You see, there are other factors that can affect the outcome, the dependent variable, the cardiovascular disease. For example, smoking status, systolic blood pressure, history of diabetes, BMI, lipid markers, alcohol consumption, educational level, occupation, among others, are factors that can also affect CVD. Just to go back with univariate analysis, we don't look at these factors. Now, when we look at these factors to determine the exact relationship between height and cardiovascular disease, all those other factors that we mentioned a while ago need to be controlled in the analysis. And when you control them in the analysis, you will be doing a multivariate analysis. So that's the meaning of multivariate analysis. So let's give an example of another multivariate analysis or univariate first. This is the objective, and this again is an analytic objective to determine the predictors of myocarditis among patients with dengue, hemorrhagic fever. And here, the independent variables are the predictors. And there are many independent variables, the predictors. It could be the age, sex, BMI, laboratory parameters, etc. Or physical examination. These are the independent variables. Now, to answer this objective, initially, a univariate analysis will be done. Each of the identified predictors will need to be analyzed one at a time, one predictor at a time in the univariate, and that is univariate analysis, looking into BMI and myocarditis one at a time, and then sex with myocarditis, age group with myocarditis one at a time, one predictor at a time. That is univariate analysis. With multivariate analysis, all variables, so after doing a univariate analysis, a multivariate analysis will then be done. And with multivariate analysis, all variables identified in the univariate analysis that could be seen as possible predictors to myocarditis, and we say that these are possible predictors to myocarditis if the p-value is not that large, up to 0.3, I normally use 0.3 up to 0.3 p-value, then these possible predictors will have to be analyzed in the multivariate analysis, meaning all variables analyzed simultaneously. Again, with univariate analysis, one variable at a time, one predictor variable at a time. With multivariate analysis, we talk of many variables analyzed simultaneously. Now, let's move on to identifying statistical tests to use. Now, the statistical test to use in a study, in an objective depends on two important information: the data classification and the type of relationship of the variables. Okay, different data classification entails different statistical tests. So we need to know what are the classification of data, because as we said, different data classifications entail different statistical tests, and we have discussed to you the different data classifications. Now, with data, just a little review, we know that data are classified as either qualitative or quantitative. And then another type of information is the type of relationship. And in the type of relationship, we have the independent variable, that's also known as the determinant or the predictor variable, and the dependent variable, that's also known as the outcome or the response variable. Now, the independent variable is presumed to cause, to affect, to influence, to stimulate, predict an outcome. The outcome is the dependent variable, and the dependent variable is the result or the outcome in its relationship with the independent variable. When we have an objective, we need to identify what is the dependent and what is the independent variable. Now, oftentimes, it's easy to tell what is the dependent and what is the independent variable. For example, when we talk of lung cancer and smoking, we know right away that smoking is the independent variable and lung cancer is the dependent variable. Okay. Now, at other times, however, we need to know the objective of the study to determine which is the dependent variable and which is the independent variable. And that is why, as I said, we need to know the objective of the study. So this is the objective of the study. For example, prior to giving the objective malnutrition and measles, we won't be able to know what the independent and what the dependent variables are, because we don't know yet what the objective of the study is. If the objective of the study here, measles or malnutrition, can assume as either dependent or independent variables depending on the objective of the study. If the objective of the study is determining factors related to severity of measles, then malnutrition is the independent variable, meaning if you are malnourished, you're more likely to develop measles, and measles is the dependent variable. If, on the other hand, the objective of the study is determining factors associated with malnutrition, so then malnutrition becomes the dependent variable. If you get measles, you're more likely to be, that's a factor, measles is the independent variable, you're more likely to have malnutrition. So malnutrition is the dependent variable in this particular objective, and measles the independent variable. Okay, so we need to know as well, with statistical tests, we need to know that there are such a thing as a parametric statistical test and non-parametric statistical test. Okay, with parametric statistical tests, they involve specific probability distributions, meaning outcomes should be normally distributed. An estimation of the key parameters of that distribution, so for example, mean or difference in the mean from the sample, and they have to be, as I said, normally distributed. Now, parametric test is used when variables are measured in the ratio scale. I hope you can still remember what ratio scales means. Non-parametric tests are sometimes called distribution-free tests because they are based on fewer assumptions, meaning they do not assume that the outcome is approximately normally distributed. Now, and we use, just to go back, we use non-parametric tests. If the scale of measurement is either nominal, ordinal, or interval scales. Okay? With ratio, we talk of parametric tests. Okay? Now, let's move on to the statistical test. What statistical tests we need to use given a particular research objective. And so this is the basic principle that I would like you to, well, somehow memorize. It's not really difficult to memorize. It's easy to memorize. Okay. If both the independent and the dependent variables are qualitative, so you need to know what the independent and what the dependent variables are. And if both the independent and the dependent variables are qualitative, the statistical test to use is a chi-square test. Now, odds ratio, prevalence ratio, and risk ratio may also be used depending on the type of the study. Now, if the independent variable is qualitative and the dependent variable is quantitative, t-test for two means may be used interchangeably with ANOVA. So we can either use t-test or ANOVA. But some people don't want to use ANOVA. They just want to use t-test. That's all right. So we can use t-test. Now, if there are more than two means to be tested, then t-test can no longer be made. The only statistical test to use is ANOVA. Now, if the independent variable is quantitative and the dependent variable is qualitative, we just reverse that, then simple logistic regression is used. And lastly, if both are independent, both independent and dependent variables are quantitative, simple linear regression is used. Pearson's correlation coefficient can also be used when we talk of correlation. Okay, so this should come handy. So we have here the independent variable You can take a picture of this one and then put it in your phone. So you have in your phone. Then if you won't be able to memorize this, but it's easy to memorize as I said. So we have here independent variable and the dependent variable and the statistical test to use. If the independent variable and the dependent variables are both quantitative, chi-square test will be used. And then the prevalence ratio, the risk ratio, or the odds ratio can also be used, again, as I said, depending on the statistical test that we will use. Now, if both the independent and the dependent variables are quantitative, then simple linear regression is used. Okay, so both qualitative, chi-square test, both quantitative, linear regression, simple linear regression is used. Pearson's correlation can also be used. Now, if the independent variable is qualitative, the dependent is quantitative, t-test or ANOVA. T-test or ANOVA. But if the independent variable is quantitative, the dependent is qualitative, you just reverse this to then logistic regression is used. We'll give now examples. Okay. So both the independent and dependent variables are qualitative, and we said that the statistical tests to use can be chi-square, prevalence ratio, odds ratio, and risk ratio. Now, prevalence ratio is used for when the disease, for cross-sectional studies, risk ratio for cohort studies, and odds ratio for case control study. But odds ratio can also be used in both a cross-sectional study and a cohort study. But in a case control study, you only use odds ratio. So let's give an example to compare the incidence of neonatal sepsis among premature babies with one group of babies breastfed fully and the other bottle-fed. So two groups of babies, one breastfed and the other bottle-fed. We look into the incidence of neonatal infection. The independent variable here will be the type of feeding, either breastfed or bottle-fed, and the dependent variable is neonatal sepsis, present or absent. So both the dependent and the independent variables are qualitative, and so we use chi-square test. Okay, now if data come from a cross-sectional study or a cohort study, then prevalence ratio or risk ratio can be used, or even odds ratio can also be used. Now if data come from a case control study, only odds ratio is used. So again, just to repeat, odds ratio can also be calculated in a cross-sectional or in a cohort study. Okay, now we have qualitative independent variable and quantitative dependent variable. Quantitative dependent, the statistical test to use is t-test or ANOVA. Now, let's give an example to determine the relationship between high school grade and sleep-wake schedule. Here, the independent variable is sleep-wake schedule, measured as less than 6 hours of sleep and 6 hours or more. So you will note that sleep-wake, if it is measured in hours, it should be quantitative. But if you categorize sleep-wake schedule as less than 6 hours or 6 hours or more, the independent variable now becomes qualitative. So qualitative independent variable. The dependent variable is high school grade measured as average grade in percent, so quantitative. So the statistical test to use is t-test for two means. T-test for two means. Why two means? We have mean for less than 6 hours and another mean for 6 hours or more. That's the meaning of t-test for two means. T-test for two means can also be called t-test for two means is also called an independent t-test or a student t-test or a student t-test. Okay. Now, when there are more than two means to be compared, so there are more than two means to be compared, then ANOVA is used. We can no longer use the t-test because, as we said, the t-test is only used for two means. But if we have more than two means, meaning more than two groups to be compared, then ANOVA is used. So let's give an example. Again, going back to the objective, but now same objective a while ago, but now sleep-wake schedule was measured as, or was categorized as, less than 6 hours of sleep, 6 to 8 hours of sleep, and more than 8 hours of sleep. So we now have three categories for the independent variable. Because we have three categories, more than two categories, we will now use ANOVA. Now, let's talk of a paired t-test. When comparing two means for measurement done twice for the same sets of participants, you compare two means, but now you compare them for the same sets of participants, and then the statistical test to use is a paired t-test. As I said a while ago, when we talked of t-test, we talked of independent. We said that the t-test is also known as the independent t-test. It is called independent t-test because the two groups are independent of each other. So those who sleep for more than 6 hours and those who sleep for less than 6 hours are different sets of participants. But if we are talking of same sets of participants, and then we will use now the paired t-test. So for example, we want to look into swimming. If swimming can increase the PFR of asthmatics, PFR is I forgot now. PFR is anyway. So we will calculate for the pre-swimming PFR. So we calculate the PFR of participants before swimming. And then we ask the participants to swim for about 30 minutes. And then after 30 minutes, a post-swimming PFR is again taken. So we will compare the before and after PFR, before and after PFR for the same sets of participants. These are the same sets of participants. The mean for the pre-swimming and the mean for the post-swimming PFR come from the same participants. I don't know why I forgot what PEFR means. Anyway, now when we compare means measured more than twice, so we use the repeated measures ANOVA. So the paired t-test, you measure them, you measure the means twice. But when you measure means more than twice, we compare means measured more than twice, we use the repeated measures ANOVA. Let's give an example. We want to look into whether an exercise, a special form of exercise, is can decrease the BMI of obese patients. So you want to look into this intervention, whether it can decrease BMI of obese patients. So we have BMI at baseline before the exercise, and then people now will do the exercise, the intervention. 1 month after, we calculate for the BMI again, we measure for the BMI, and then after another same exercise will continue at 3 months, at 6 months, and then at 12 months later, there will be several measurements. And so we have repeated measurements of the BMI at baseline, at 1 month, at 3 months, at 6 months, and at 12 months. So we have repeated. The statistical test to use is a repeated measures ANOVA. As long as the measurement is done more than twice, and then we use the repeated measures ANOVA. Now, when the dependent variable is qualitative and the independent variable is quantitative, we use the logistic regression. So let's give an example. We want to determine the relationship between BMI and osteoporosis. Here, the independent variable is BMI, and we know that BMI measured as in kilograms per meter squared is quantitative. And the dependent variable is osteoporosis present or absent, and so the statistical test to use is logistic regression. Now, lastly, both the independent and the dependent variables are quantitative. We use linear regression. And as I said, Pearson's correlation coefficient can also be calculated. Okay, so let's look into an example. This is the objective of the study, to determine the relationship between cholesterol levels and blood pressure. So the independent variable is cholesterol level measured in grams per deciliter, so that's quantitative. And the blood pressure in millimeters mercury, again quantitative. Both are quantitative, and so the statistical test to use is linear regression. Okay, now let's move on to non-parametric tests. With non-parametric tests, as we said, variables are not normally distributed. And as I said a while ago, the variables are measured in either the nominal scale or in the ordinal scale or in the interval scales. Okay, so again, this should come handy. Here we have the independent variable and we have the dependent variable in the statistical test. Now, let me just emphasize to you that when we talk of non-parametric tests, all independent variables are qualitative. All independent variables are qualitative. That is why I'm not talking here of whether it's quantitative or qualitative. So all independent variables are qualitative. We just classify them, the independent variables, as to whether we have a two-category independent variable, two-category independent sample. We talk about independent sample, meaning they are not, the categories are not related to each other, or they are not matched. So we also have two categories. We have two categories and they are matched, meaning very much like the paired t-test, we are talking of the same sets of participants. When we are talking of matched or related, we are talking of the same sets of participants. When you say independent sample, just like an independent t-test, the two categories are independent of each other. Okay, so first, we have two categories, independent, they are independent, and the dependent variable is nominal. So very much like in a chi, so the statistical test is chi-square test. So you will note, just to remind you, I mean just to give you the review you. So the independent this is qualitative, the dependent is also qualitative, that's nominal qualitative, and then the statistical test is a chi-square test. We use the Fisher's exact test when the sample size is very small. The sample size is very small. Now we have two categories and they are matched or related. We are talking of the same sets of participants. And then the dependent variable is a nominal, or qualitative nominal. And then McNemar change test will be the statistical test. Let's give an example. I won't give example anymore for the chi-square test because we already gave an example on the chi-square test a while ago. We'll give an example of the McNemar-Chains test. Okay, so let's look into the comparison of the level of self-esteem before a counseling session. So, for example, we have two groups of people with self-esteem. So, and then you do counseling session, and so you measure the number of people who have low or high level of self-esteem before a counseling session and after a counseling session. So we look into the people before the counseling session, how many of them have low or high self-esteem, and how many of them after you do the counseling, you determine how many of them have low or high. So you compare the number of people who have the level of self-esteem, either low or high, before and after. So this is nominal, low or high is nominal, and so the statistical test to use is a McNemar-Chains test. Now, if we have K categories, when we say K categories, we mean more than 2 categories. And these categories are independent of each other. They are not related. They are not of the same participants. These are different participants. When say independent, again, these are different participants for different categories. And then the dependent variable is nominal. Again, chi-square test, because this is just the independent is qualitative, the dependent is also qualitative. We use the chi-square test. Now, for K categories, but they are related to each other, they are the same participants, you measure them more than 2 times, and the dependent variable is nominal, then the statistical test is a Cochrane Q test. You will note that if you have 2 categories matched, this should be McNemar-Chains test. But if you have 3 categories, they are talking of the same sets of participants. Okay, you measure them more than twice, we use the Cochrane Q test. Again, we won't give an example of a chi-square test. We'll give an example of the Cochrane Q test. So, level of self-esteem before a counseling session, same objective, but now we have many levels, many measurements. So, before a counseling session, after a counseling session, after a second, after a third counseling session. So you measure level of self-esteem 4 times: before the counseling session, and then after the first counseling, after the second, third, and then after the third, fourth. So 4 times you measure them. So more than twice, level of self-esteem is low or high. The statistical test to use is a Cochrane Q test. Now, 2 categories, independent samples. So again, 2 categories, they are independent of each other. And then the dependent variable is ordinal, not nominal anymore, ordinal. Mann-Whitney U test is used. But if the 2 categories are matched or related to each other, these are the same participants, you measure them twice, and then the dependent variable is ordinal, and then we use the Wilcoxon sign ranks test. We'll give example for these 2. Okay. Well, just to review you, here 2 independent samples, and this is ratio. We use the paired t-test, and that is why we use the t-test, the independent t-test. So the independent t-test is the counterpart in the parametric test of the Mann-Whitney U test, or rather, let me rephrase that. The Mann-Whitney U test is the counterpart of the independent t-test, of the independent t-test in the non-parametric test. So let's give an example. Comparison of pain scale from 0 to 10 using drug A versus drug B. So you have two groups of people, one given drug A, another one given drug B. Okay? And then you compare the pain scale of these people. So these are different people. Those given drug A are different from people given drug B. Okay? And this is an interval scale. Okay, just go back. This could be either ordinal or interval. This could be either ordinal or interval. Okay, and then the statistical test to use is Mann-Whitney U test. Okay, now Wilcoxon signed ranks test. This is the Wilcoxon, well, the counterpart of a paired t-test in a non-parametric test. Okay, or rather, I should say, Wilcoxon signed ranks test is the counterpart of the paired t-test in the parametric test. For non-parametric test, Wilcoxon signed ranks test. So we now talk of comparison of pain scale before and after an intervention. So you are talking of the same sets of participants. You note that paired t-test, you talk of the same sets of participants. So we are talking of the same sets of participants. You measure them twice. So before and after an intervention, you use the Wilcoxon signed ranks test. Now, okay, so we have K categories, K categories, but they are independent, and the dependent variable is either ordinal or interval. Statistical test to use is Kruskal-Wallis. Okay, but if these categories, you are talking of the same sets of participants, you measure them more than twice, K categories more than twice, and then the dependent variable is ordinal or interval, we use the Friedman's test. Let's give an example. Well, again, Kruskal-Wallis is the counterpart of ANOVA in a non-parametric test. So, in a non-parametric test, it should be Kruskal-Wallis, but if it is parametric test, we use ANOVA. With ANOVA, we have many. Notice that we have many categories. More than two categories. With ANOVA, we also have more than two categories. Okay, so comparison of pain scale from 0 to 10. This is interval among people given drug A, drug B, and drug C. We have three groups of people. They are independent of each other, and because we are talking of an outcome, the dependent variable, which is pain scale, that's ordinal, we use Kruskal-Wallis. Now, Friedman's test, we use the Friedman's test. This is the counterpart of repeated measures ANOVA. Repeated measures ANOVA in parametric test. Non-parametric, that's the Friedman's test. So, let's give an example. Determining whether type of music affects. You want to determine whether type of music affects the perceived effort to exercise. We have 10 participants. You ask them to run on a treadmill for 30 minutes for 3 consecutive days. So we'll be talking of the same 10 participants. We ask them to run on a treadmill for 30 minutes for 3 consecutive days. Now, in a random order for 3 days, each participant runs. So one participant runs first day listening to no music at all, second day listening to classical music, third day listening to dance music on the third day. Now, another participant runs first day listening to classical music, second day listening to dance music, third day listening to no music. Still another participants listening to dance first day, second day no music, third day classical music. Still another participant listening to classical music first day, second day no music, third day dance music, and so on and so forth. So each of these 10 participants in a random order for 3 days runs using the 3 different types of music or for 3 days. Now, at the end of each run, each day, subjects are asked to record how hard running session felt on a scale of 1 to 10, 1 being easy and 10 extremely difficult, extremely hard. Now, so we use there, when we do statistical test, we use the Friedman's test. We combine all those who run using no music, look into, of the 10 participants, no music, scale of 1 to 10. So get the mean, okay, and then again among those who run with classical music, combine them all 10, and then all those who ran with dance music, again get the mean, then compare the mean for the 3, because these are nominal scale or ordinal scale of measurement. We use the Friedman's test. As a matter of fact, we don't use the mean when we calculate for the Friedman's test. We use the rank sum. We rank the sum. But I won't explain to you how that is calculated anymore. I just want you to understand what statistical test to use given that objective. Now, okay, when we talk of measures of association, so when we have the independent variable being nominal and the dependent variable also nominal, we use a measure of association, the kappa coefficient or the Kramer coefficient. But for both ordinal and ordinal, we use the Spearman rank or the Kendall tau. But for quantitative, we said Pearson's correlation coefficient. Okay, let's talk of other tests to determine a cutoff, to make a diagnosis of a disease, to predict an outcome. A receiver operating characteristic ROC curve is done. So if you want to determine a cutoff, a receiver operating characteristic is done. For survival analysis, we use the Kaplan-Meier and then the Cox regression. Kaplan-Meier for univariate analysis and Cox regression for multivariate analysis. Now, in survival analysis, just want to tell you that there is censoring, time to event not observed, and we have an equal follow-up of time. So examples, chemotherapy and time to death, and then surgery versus medical and time to recovery. These are just examples. We use the Kaplan-Meier or the Cox regression. In clinical trials, we calculate for the risk ratio, the absolute risk reduction, the relative risk reduction, number needed to treat, number needed to harm. They are all calculated. And then other tests, we use Poisson regression when the outcome, the dependent variable, is a count within a given period of time. So, for example, we want to look into the number of people developing a disease after exposure to a risk factor. So, the outcome is a count. We use Poisson regression. Okay, I am about to end. We just talk about some tips later on when you make your research proposal. For each objective, identify the statistical test to use. And we said that in identifying the statistical test, we need to know the data classification and the relationship between variables and then their data classification, whether it is the independent or the dependent variable, what are the data classification for the dependent and independent variables. So this data classification and this relationship can be seen from the objectives of the study. Then you will be able to know the data classification from the operational definition. So we need to look into the operational definition to be able to know the classification of the variables. And then sample size calculation must be consistent with the objectives of the study. When we talked of sample size calculation, we talked of the objectives of the study. So we calculate for the sample size, just to repeat what I have discussed earlier. Okay, just to repeat that sample size calculation is done based on the objectives of the study. And the statistical test that we use will be consistent with the objectives and the sample size. And dummy tables must be consistent with the objectives and statistical test. All five have to be consistent. The objectives, 1, operational definition, 2, sample size calculation, 3, statistical analysis, 4, and dummy table. They all have to be consistent. Okay, let's give an example. Okay. To determine the relationship between, there is no between here, between pregnancy interval and risk for infant mortality. Okay. Here, the independent variable is interpregnancy interval, and the risk for infant mortality is the dependent variable. So we will now look into the operational definition. The independent variables, as we said, is interpregnancy interval, defined as time between the last live birth and the date of conception for the current live birth. So when we talk of time between the last live birth and the current live birth, we are talking of quantitative data. But if you talk of, it will be dichotomized to, so it will be recoded to less than 18 months short and 18 months and above appropriate, and the independent variable, which is originally measured quantitatively, is now recoded as to whether it is short or appropriate. Then the independent variable interpregnancy interval is now qualitative. Now, the dependent variable is risk for infant mortality, defined in terms of time of delivery, birth weight, infant's gestational age. And so, based on these three parameters, time of delivery, birth weight, and infant's gestational age, and it will be classified as having risk or not having risk for infant mortality. So when we say, again, the time of delivery, birth weight, and gestational age, they are all quantitative, but if you classify them as having risk or not having risk, this now becomes qualitative. The dependent variable now becomes qualitative. And we need to define operationally what does having risk and not having risk for infant mortality mean. Okay, so having risk for infant mortality is defined as anyone or a combination of preterm delivery, so combination, anyone or a combination. So you will note that it is or anyone or a combination of preterm delivery before 37 weeks, low birth weight, less than 2.5, and small for gestational age, below the 10th percentile. So this is the having risk. So anyone or a combination of infants having this criteria, before 37, low birth weight, and small for gestational age, they will be classified as having risk for infant mortality. Now, not having risk is defined as term, so 37 and above, normal birth weight greater than 2.5 and above, and appropriate beyond 10th percentile. So appropriate, there is nothing abnormal, so not having risk for infant mortality. Okay, so since our dependent and independent variables are both qualitative, the statistical test that we will use is chi-square test. So with sample size calculation, okay, so with sample size calculation, sample size was calculated based on the comparison of the incidence of risk for infant mortality among mothers with short and appropriate inter-pregnancy interval. So comparison of incidence of risk for infant mortality among those with short versus appropriate. And then continuation of the sample size, assuming that mothers with short inter-pregnancy interval, among them, incidence of risk for infant mortality is 46.8, and among those with appropriate 37.1, and I got this from this author in 2012 with an alpha error of 5, power of 80, one-tailed, sample size calculated is 318 per group or 636 for two groups. Now, controlling for 5 more variables in the analysis with an additional 20% for each control variable, final sample size is 1272. We discussed this when we talked of sample size calculation. Now, what statistical test do we use to determine the relationship between inter-pregnancy interval and risk for infant mortality? So, chi-square test will be used, odds ratio, and the 95% confidence interval of the odds ratio will also be calculated. Okay, control variables will also be examined. We need to do multivariate analysis. Control variables will also be examined for their relationship with risk for infant mortality, first in the univariate analysis using chi-square test and logistic regression for qualitative and quantitative independent variables respectively. So for qualitative, chi-square test; for quantitative independent, logistic regression. Okay, and then a multivariate analysis will then be done using multiple logistic regression. So with when we talk of multivariate analysis, our outcome is qualitative. We now use the multiple logistic regression. Level of significance will be set at alpha equals 0.05. And this is the dummy table. So having risk for infant mortality for short and appropriate inter-pregnancy interval, number percent, and then the odds ratio estimate and the 95% confidence interval. Then I have here a note, chi-square test is used. And then this one now, again, so these are other control variables in the multivariate analysis. So we have the crude odds ratio for univariate and the adjusted odds ratio for the multivariate analysis. So you will note that all 5 are consistent. The objectives of the study, operational definition, sample size calculation, statistical test, and lastly, dummy table. All 5 are consistent. And I think that's the end of this lecture on statistical analysis. I hope you're able to understand, have a good idea of what statistical analysis is all about, and be able to know how to write statistical analysis given the objectives of that study. Thank you.